so let's get to it. The first thing I wanted to do just real fast is to talk about, so you remember on Friday I broke math? Well, I figured out my error. It's actually really, really funny once I figured it out. So the problem basically came down to my crappy drawing misled us. Okay, so let me pull back up the drawing that I made last time, right? So, perfectly reasonable sketch? Not quite. And that was the problem. So here's what it's supposed to look like. Okay. Um, Before I realized that it was a bad sketch, well, basically the first thing I did was I sat down and I actually used I actually calculated the center of mass using the formulas for it. And uh, in this case, so because of the symmetry, I can say that the x and the y coordinate of the center and mass would be the same. Okay. What I messed up on the symmetry was to say that it was, I mean, look at my picture from last time versus what it is here, right? So if you look at it here, what do you see? It's a little bit fatter at the bottom left than it is at the top right, okay? And so we should expect that the center of mass is slightly more towards the bottom left than it is towards the top right, okay? Seem reasonable? So here's where the center of mass, I thought it was at 1/2 comma 1/2. Guess where it actually is? It's at 9/20 comma 9/20. Okay, so let me let me actually draw a couple things. So um, I didn't even have to go ask Professor Brown. Actually, here, let me put P3 first, so I still get the axes. Okay, so the this is where I thought it was. That's actually where it is, right? And that was enough to make the difference, because if it's at 9/20 comma 9/20, okay, so it's 9/20 units away from the axis. So if I spin the thing, the radius is 9/20. So what's the circumference of the rotated object, or the rotated thing? It would be 2 pi times 9/20, right? Okay. And what did we get for the area of that contraption? I thought we got 1/3. Did that sound right? Yeah. Um, oh, yeah, it's over there, right? So if I do that, right, 2 pi times 9/20 times the 1/3 the area, I get 3 pi over 10, which, haha, that was the volume that we calculated the other two ways, right? Okay, so I didn't break math, I just am incompetent, but you guys knew that, right? All right, anyway, uh, so let's get back to today's stick. So let me go back to the Elgato. I want to pull up the stream on here so I can actually see how things are going. All right, so the topic du jour is arc length and surface area. And so the first off, let's start with arc length. So the formula for it is this, and we'll kind of talk about why. Okay, so if I take the square root of 1 plus the square of the derivative and square root that whole thing, if I integrate that, that will give me the arc length. Now here's sort of the idea as to why that's the thing that we integrate. If I imagine drawing a curve, right, and I pick a point on it, I'm going to draw a really tiny triangle. Okay. And what is the slope of the tangent that I just drew? It's whatever the derivative is, right? So I can think of, say, having a triangle which has dy and dx as its sides, okay? But I could also think of it as one unit this way and dy dx units that way, okay? Do you guys agree that those two triangles would be similar? Because what's the slope, which in this case happens to be the tangent of that angle? What's the slope here in the first triangle? Rise dy over run dx. Okay, so there I'd be treating them as differentials. On the second triangle there, well, what's the slope of that hypotenuse? It'd be the rise dy dx divided by the run, which is 1. Same thing, right? Okay, so in the second triangle, what is the hypotenuse? Well, Pythagoras' theorem certainly applies, right? I got a right triangle. And so can I just square root both sides? So I get that. Okay, so that's basically the idea. I mean, I'm sweeping a few details under the rug, but that's essentially it. Yeah.
So since we're getting the derivative of that arc, so the reason we're taking the integral of it is to get the actual arc itself.
The length of it, yeah. So the derivative kind of tells me the slope at any given point, right? And so I'm not integrating the derivative because that wouldn't do anything. It would just get me back to the original function. What I'm integrating is this expression, this square root stuff, that is in terms of the derivative, right? And that basically what I'm doing is the thing I'm integrating is an infinitesimal little like piece of the, well, okay, so here's basically what I'm doing in an approximation sense. You know, it's kind of like, how did we approximate the area enclosed by a region? We divided things up into little rectangles, okay? Well, if I've got some curve, could I approximate its length by picking a bunch of points, okay, like I do with the area stuff, but then saying, okay, I'm going to connect them with straight line segments, say, and calculate the length of each of those line segments?
I mean, yeah, but like, how does the integral of the derivative give you the length of the arc?
Oh, it's not the integral of the derivative.
Or how does using the derivative in the integral?
Okay, so if I wanted to know the length of, say, the blue, red, and green segments, right? I would need to know, um, well, in this case, what do I need to know to compute the length? I need to know the coordinates of these 2 points, right? Well, so that I could do Pythagoras' theorem, and then I'd need to do the same for the red line and the green line and so on. Okay, Well, it turns out then that the formula, like if I sit down and I actually write out the approximation for that, and then I so let me call this quantity here delta x. Okay, kind of like we did in the area, so the width of each, or the space between each point, right? Well, if I sit down and I write out what is the sum of all of these distances, and I stare at it for a minute, and I let delta x go to 0, well, okay, so let me rephrase a moment. If this, let's take the blue segment there. If the distance between those 2 points is a finite positive quantity, then how many points do I have for the blue segment to determine its length? I've got 2, right? One at either end. Okay, great. But what happens if I take the width, delta x, and I take a limit of it as it goes to 0? What's going to happen to the 2 points that define my blue segment? They're going to get closer and closer and closer, and so in the limit, what really is happening? They're becoming the same point. Okay, well, that's exactly what the derivative does, right? What is the definition of the derivative? It's the limit of the slope of those secant lines, right? So that's why it turns out in the formula. Okay. All right. So let's actually take like the world's stupidest example, okay, of this in action. Okay. And what would be the world's stupidest example for something like this? Well, yeah. Let's use this to find the length of a straight line. Right? I mean, we could, right? Okay, so what 2 points? What let's do y equals. Oh, I don't know. Let's do y equals x from x equals 0 to x equals 1. Okay. Uh, okay. We're not idiots, so the answer should be the square root of 2 by Pythagoras' theorem, right? Okay. Well, let's set up the integral and make sure that that's what we get. Well, here I'd integrate from 0 to 1. What is the derivative in this case? 1. And so I get that, right? So if we were morons and decided to use this to find the length of a known object or a straight line, we ought to get the same answer as if we just did Pythagoras' theorem, I would hope, right? And sure enough, we do. Okay, is that Gucci? Yeah? All right, well, let's take another one. Let's take one that's not quite so easy. Do you guys mind if I move to a new sheet? Is it okay? Good. Okay. Let's take y equals x squared. Okay, so this, by the way, would be to calculate uh, in the previous the example that we were looking at the very beginning, right, of how I broke math on Friday or actually didn't. This would be equivalent to calculating the length of that blue curve, or for that matter, the orange curve, because they're the same length. Okay. All right. So what's the derivative here? 2x. Good. And so what I would need to integrate would be this, right? Because if the derivative is 2x, what's that squared? 4x squared. And it's 1 plus that because that was the arc length formula. So that's the integral that I got to do. Okay, good. How do I do that integral? Oh. Okay, those of you who are at home can't see what I'm about to do. No, it's 3 feet, but bad student. Yeah. Okay. Yeah. Yes, exactly. Um, the beating shall continue until morale improves. Right. Okay. So, yeah, how am I going to actually do that integral if I wanted to? Oh, yeah, it was real easy last time. Okay. Well, first thing I'm going to do is actually factor out that annoying 4. Um, and I'm going to think of it like this. I'd have to do trig substitution, right? With x equaling a half tangent theta. Okay. And so what's dx? Col. Thank you. That's why I gave you the ball, man. Yeah, the math gym. Actually, it's not a outrageous metaphor, right? Right. If you're taking a weightlifting class and your final exam is to bench press 200 pounds or something, I don't know, right? Then and you just sit around and watch the coach bench press every day that you go to this class, what's going to happen when you get to your final? You're not going to be able to bench press 200 pounds, right? You have to be the one sweating. Yeah. Anyway, all right, so that, right, and so our integral, we'll deal with the bounds later, would be well, actually, you know what? Let me go back to the original version. Um, because oops, and I forgot the differential. Okay, so the square root quantity is just secant right after you square root it, because I've got 1 plus tangent squared is secant squared, and I square root that thing, I got secant. So this is 1/2 the integral of secant cubed. Now, how do we integrate secant cubed? Yeah, okay, write it as secant and secant squared. And then I'm going to let u equal secant, dv equals secant squared. Then du is secant tangent, and v is tangent. So then I have 1/2 uv minus the integral of v du. Right? Well, what's tangent squared? right? Does this look familiar? This is the one where we have to add it back to the other side. Okay, so we have 1/2 the integral of secant cubed d theta is equal to 1/2. Oh, I lost a tangent. 1/2 secant theta tangent theta minus the integral of 1/2 secant cubed theta minus 1/2 the integral of plus, sorry. Okay. And so I'm going to add the secant cubed to the other side. And then, of course, we all remember that the integral of secant is the natural log of secant plus tangent, right? Yeah? Okay. All right, so that's the integral of secant cubed, which is, so our arc length is 1/2 that. Okay, so we now have, so arc length is a 1/2 of that. All right. All right, now, that's in terms of theta, but we got to get it back in terms of x, right? So let's go back. What was our substitution? We let x equals 1/2 tangent theta, right? So that means that 2x is tangent theta. So I could put a 2x here and a 1 there, and then that makes this, not shockingly, that, right? Okay, and so then here's my angle, and I need secant and tangent. So secant is 1 over cosine. Cosine in my triangle is 1 over the square root stuff, so secant is the square root stuff over 1. Tangent, we said, was 2x. And then, okay, so that's the arc length integral. But now I have to plug in 0 to 1 in it because that's the points in question. Okay, all right. When I plug in 0, what do I get? This term, the first term is definitely 0 because I got that x there. But the second term also is 0, and that's because that's 0. If I put 0 in here, I get 1 on the inside of the logarithm. What's log of 1? 0. Okay, so I only have to plug in 1 here. And so what do I get? I get 2 over 4 is 1 over 2 square root of 5 plus 1/4 natural log of 2 plus the square root of 5. That's pretty ugly. Yeah, and in fact, while we're at it, let's, oh, you really had to give me arccinch? Seriously? So, you know, sine and cosine, right? Those are defined in terms of the unit circle. Well, could we define things in terms of the unit hyperbola instead? And you get the hyperbolic trig functions.
Wait, but where's the hyperbola stop?
It doesn't.
So you're saying like,
Well, if only there were a task and a section in the book all about hyperbolic functions, right? Yes, so it's just a high, whatever. Okay, yeah. All right, so we get whatever. It's 1.4, blah blah blah. Yeah. Now, just for sake of example, uh, the a straight line distance would be square root of 2, right? Well, what is the square root of 2? 414, right? All right, so that actually feels something doesn't feel quite right there. No, just seems like that's a little longer than the straight line distance than 0.06. Um, well, whatever. I mean, it is what it is. Okay, so yeah, so if we just sort of numerically approximate this, we get whatever. Wasn't that kind of a pain in the butt? Yeah.
So, if the interval is like, if the bounds are like 0.2 to 1, would you subtract this one we got from the other one?
Yeah.
Okay.
So in this
This is
case,
just subtracting zero, so it's pointless.
right, and so I didn't bother. But yeah, if I had two non-zero things, then yeah, I'd have to do more arithmetic. Okay, wasn't that a pain in the butt? That was just for x squared. Okay, so let me just say I wanted to do the same thing for x cubed. Well, then I would need to do this integral, right? Do I know how to do that integral? If it were x squared, we'd be in business, but it isn't. It's x to the fourth. All right, well, let's make the machine do it.
Should we write this down or is this too?
Uh, no, go ahead. All right, so if you want. Oh, that was really illuminating. Of negative one half, comma one fourth, comma five fourths, comma negative nine. Well, it is. Okay. So the point here is that, so you remember we talked about special functions previously? This is a special function, meaning like there is no antiderivative that I could write down in terms of elementary functions.
Right.
Okay. So we're hosed.
So you mathematically can't calculate what the arc length is?
Not exactly. I could certainly do it numerically, right? So I've got this integral, right? And we've talked about all kinds of numerical methods for how to approximate integrals. We could throw one of those at it, right? And if all I want to do is get an approximate answer, that's good enough. Okay, so the reason I brought this up is that one of the things that I hate about the arc length formula is that for very simple shapes, the arc length integrals are impossible.
So why'd you hit me for saying use a calculator?
Huh?
Why'd you hit me for saying use a
Because
calculator?
you said it at the wrong time.
Oh, why don't we use a calculator?
Huh? Well, now we certainly would, because I don't know what the hell hypergeometric 2f1 of blah is.
Because it changes like on x squared, it didn't change like its direction. Like when it's going up.
That actually wasn't a problem because x cubed doesn't either on that interval, right?
Oh, that's true.
Right. Now, if I change the interval, then okay, whatever. But really, it doesn't matter because the formula, the thing that we need to integrate, is such a pain,
Uh-huh.
right? So all this to say that the simplest looking curves, their arc lengths can be either exceedingly difficult or outright impossible to calculate. That's really annoying, but them's the breaks. Yeah, Jack. It's a special function, right? So, and I mean special in a technical sense there, not that I'm just being silly, right? What does it look like? I don't know. I mean, it's in this case, right? It takes four parameters, so even graphing it is kind of a meaningless question, right? Um, because I'd have to nail down three of them and let a fourth vary to get a graph of some sort. Um, yeah. So, like, you guys remember when we did the integral of e to the minus x squared thing, right? That was probably our first example of a special function. It's not the only one. There are, of course, infinitely many out there, but yeah, it's we ran into one here. Okay. It kind of sucks, but yeah. So, salient point is arc length problems sometimes are basically impossible. Okay. And what this means for you guys, for the standards, is we have to do one of two things. Either we have to choose the curve really, really well, okay, so that it's actually possible to work it out, or we make the problem to set up the integral but then not compute it. Okay, does that make sense? Because half the time they're impossible. I'm sorry. Just it is what it is. Okay. Um, but so the next thing we can do is we can actually combine this with what we were doing the last two classes, right? So what did we do on Friday and Wednesday? We talked about if we take a curve and we revolve it around an axis, what's the volume of that enclosed object? Well, this arc length thing will give us a method to get the surface area. Okay, so the idea here is if I take a curve, so let me just draw a curve, and I imagine spinning that curve around the x-axis, okay, how did we think about the volume in this case? We thought about it by taking a little slice and finding the volume of that slice as it revolved, okay? All right, well, what about if I wanted to compute the surface area instead? What I would need to know is I would need to know that length, okay, of that little piece, the thing I've drawn in blue there, and then I would need to multiply that by um, 2 pi r, okay, because so if this sweeps out a cylinder, right, what do I need to compute the lateral area, so the side of the cylinder? Well, I need to know the circumference of the circle times the height of the cylinder. Well, the circumference I can get by 2 pi times the radius. The height of the cylinder is exactly the arc length. Okay, and so the surface area will be this. Okay, and the two parts here is 2 pi times radius, and then this part is the arc length, basically, right? Uh, yes, but uh, right, my slice here, I've drawn it really thick. But what's the whole point of integral calculus is that that's really like infinitesimally wide, and so those two circumferences really become the same thing. Okay, no, you're right. Uh, so what Cole's pointing out is that if I were to actually draw that blue thing, right, I'm not looking at the side of a cylinder, but actually the frustum of a cone. So it'd be like a cone with its top chopped off, right, where the sides would be kind of slopey. But as I take a limit, or equivalently as the number of these little partitions goes to 0, that slopey bit becomes straight. And so from an integral perspective, it's okay. Okay. All right. So there's our surface area formula. Okay. So what I'd like to do is to look at a really fun example. And let's look at the example. Well, all right. So I'll just plot this from 1 to 10. Okay. Now, in particular, I'm not going to have to worry about the asymptote, right? So x equals 0 obviously is a problem for this function, but I'm not going to worry about that because I'm going to start at 1 and go on to infinity. Okay. And in fact, let me actually. Oops. Really? Okay. So, why did it plot 0? Okay, whatever. So, great. So I'm going to take this 1 over x curve, okay? And I want you to do two things. From 1 to infinity, I want you to set up the integral that describes the volume that this thing sweeps out if I revolve it about the x-axis, okay? And I want you also to do the surface area formula. Okay, so set up those two integrals. All right, so let me go back over to the here, okay? So let's do okay. So set up the arc length and the not the arc length, the area, surface area, and the volume. Which volume method are we going to use here? Disks or shells? Definitely disks. Okay, but it's yeah. Okay, so just pause for a second, make sure you've got both integrals set up, and then look at the screen and tell me if you agree that I've also set them up correctly, hopefully. Okay, do you guys agree that I've set them up correctly? Now, the first one ought to be real easy to compute. Well, with one minor exception. What kind of integrals are these? They're super improper, right? So, so the first one, volume, Okay, so the volume turns out to be pi. Okay, now first off, we know that the integral of 1 over x squared from 1 to infinity, does that converge or diverge? Definitely converges by the p-test, right? And in this case, because it happens to converge to 1, but we've got that factor of pi, so the whole thing in this case converges to pi. All right, so what does this mean about this, this hyperbola that we've rotated about our axis? It sweeps out, even though it's an infinite curve, it sweeps out a finite volume, okay? Because that integral converged, in this case, to pi. What about the surface area integral? Well, this one's a little hairier, right? How are we going to integrate this puppy? Not quite so easy looking, is it? Right? Because what do we have? Well, again, we're going to have to think of it as that. Um, yeah. All right. Now, for the sake of time, let me cheat. And let's get the antiderivative of that thing. And then we'll, okay, it's kind of nasty. Let me actually see if it'll simplify it at all. No, it's going to be all, yeah. Okay. Yeah, this one's pretty terrible. But in particular, okay, let me take this object and let me just plot it. From 1 to 10. Okay, so if I plot this thing from 1 to 10, okay, sorry, let me switch over on the thing here. We want Mathematica. Okay. All right, so here's the antiderivative of that thing, right? We could figure it out. It would just take a little while, okay? So if I plot that thing from 1 to 10, let me plot it from, say, 1 to 100. We keep plotting it for large values. What do you guys think is happening to it as x goes to infinity? Just looking at the plots, does it look like it's settling, like it's approaching a fixed number? It kind of does, but well, okay, but look at the scale, right? What does it look like it's approaching? 11 something? Oh no, it's like 13 something. Oh no, it's like 15 or 16 something. Yes, it diverges. It has infinite surface area but finite volume. Oh, well, we would have to basically sit down and take the limit of this thing as x goes to infinity. And if we rewrote that a little bit, like, um, well, okay, so if we took the limit as x goes to infinity, it ought to be clear that this first term, what's going to first term going to approach? This square root part would just go to 1, right? Because if x goes to infinity, what's 1 over x to the fourth going to do? going to go to 0, and so I just have the square root of 1, and then that minus a half that's out front. Okay, all right, so that part is easy to deal with. As for this other contraption, okay, I mean, part of the problem is we'd have to write down what the heck arcsinch is. But that second term, right? What we've sort of discovered graphically is that the limit of that thing is not it diverges. It goes to infinity. Okay, so if we think about, well, what were we doing? We were doing an an improper integral, right? If that's the antiderivative, and we let the x go to infinity on that, then we get an infinite quantity, okay? And so the salient point, right, is that this integral, the surface area integral, diverges. It blows up to infinity, okay? So what does that mean about our original shape? Finite volume, but infinite surface area. Does that kind of, doesn't seem possible? Well, I mean, what did I tell you guys when we started talking about improper integrals? Well, when infinity gets into the mix, take your intuition and throw it out the window, right? Okay, now, this example is famous, this 1 over x example, okay? Does anybody happen to know what it's called? It's called Gabriel's horn. Huh? Well, okay, who is Gabriel? Huh? Yeah, it's an archangel, okay? So imagine he's got a horn like that he would like toot, right? Well, I mean, if he's an archangel, he's going to have an infinite horn, right? It's going to be a really, really awesome horn. Yeah. I'm actually not sure who named this after him. So let's actually use the Google. Uh, Not usually. Oh, that's right. Torricelli's trumpet, right? Is the other here. Let me switch over to Chrome so you guys online can see it. Yeah. So it's Torricelli. Okay. Well, this guy, pretty epic mustache. Yeah. So anyway, yeah. So the surface area, um, So this is the thing, right? Do we really actually care what the surface area integral is? If we could argue that it diverges, then we're Gucci, right? And we've noticed that it diverges. So yeah. Um, anyway, so that's Gabriel's horn. Isn't that freaking awesome? Yeah. No, it what do you mean doesn't work? Oh, sorry. Um, so you guys online, sorry, I didn't realize the screen's black. Um, so yeah, just here it is on Gabriel's horn. So just look at that on Wikipedia if you want to read a little bit of the history. So yeah. All right. Well, it's 9:56, so we should quit. I will see you guys next time.